for me, Dudek, and today I will tell you about our joint work with Paweł Gabrychowski and Tatiana Starykowskaja, showing that all non-trivial variants of free LDT are equivalent. First, let me describe a free-sum problem, which will be central to our presentation. So in this problem, we are given a set X of n integers, and we need to answer if there are distinct elements x1, x2, and x3 from this set, such that they sum up to 0. And usually one assumes that this universe is from minus n cubed to n cubed, and till the end of this talk, we will focus only on such a universe. Free-sum problem is a fundamental problem in fine-grained complexity because it is related to many other problems in computational geometry, algorithms on strings, dynamic algorithms, and algorithms on graphs. And clearly there is a cubic time algorithm solving free-sum because we can iterate over all triples of elements from X and checking if they satisfy this equation, but we can do it slightly smarter in n squared time. So first we sort the set X, and then we'll iterate over all elements x1. So first say this is element 1, and then we know that elements x2 plus x3 must sum up to minus x1. So we can find them using the technique with two fingers, that x2 starts with the smallest element, x3 starts with the largest element, and they move towards each other. And this algorithm runs in n squared time, and essentially there is a conjecture stating that we cannot do much better. So for any positive epsilon, this conjecture states that there is no O(n) to 2 minus epsilon time algorithm on word RAM with words of length log n. So in other words, that there is no truly subquadratic time algorithm for free-sum. And now this is really the best what we can do, because the best algorithm that we know is by Chan from 2018, who solved free-sum problem in n squared divided by log squared n times some very small factor. And this is currently the best algorithm for free-sum, and it also works for real numbers. And free-sum problem was also considered in a linear decision trees model. And first, Grunwald and Petty showed that there exists a linear decision tree of depth n to 1.5 times square root of log n with linearity 4, where linearity is the maximum number of elements from the set that we can use in a single test that we perform in a node of the tree. Later, this was improved by Gold and Sharir to slightly smaller depth of the tree with the same linearity. And very recently, there was a breakthrough result by Kane, Lovett, and Mora, who showed that there is an almost linear depth tree with linearity only 8. So this is the best what we know in linear decision trees model. But unfortunately, these results do not transfer to faster algorithms for free-sum. So yeah, that was the background. And now let me introduce a problem which is related to free-sum, namely average. In this problem, we are also given a set of n integers, and we need to answer if there are distinct elements such that the sum of two numbers is twice the third number. Or in other words, we need to check if the set X is progression free, because these three elements, this equation says that the three elements form an arithmetic progression. And we know that there exists a reduction from average to log n instances of free-sum. So this gives us that average is not more difficult than free-sum. So it even seems that average is easier than free-sum because we can solve average with free-sum. And what if indeed free-sum is more difficult than average? And this was discussed by Jeff Erickson in 1999, when he said that then it was not known whether average is free-sum hard, and maybe we should say that the free-sum hard problems are called average hard, because this is a apparently slightly easier problem, which we still cannot solve faster than in quadratic time. So the main question that arises here is that, can we reduce free-sum to average? So then this will give us that these two problems are equivalent, but we don't know how to do it. So let me expand the mysterious abbreviation LDT. It stands for linear degeneracy testing. And the main formulation is as follows. So we are given integer coefficients, alpha 1, alpha 2, alpha 3, and t, set x of numbers, and we ask if there are distinct elements x1, x2, and x3 belonging to x, such that this linear combination sum up to t. And clearly this formulation is a generalization of both free sum and average, because we can set appropriate values of alphas and obtain one of these two problems. Okay, so that's the definition of free LDT with some parameters, but this is one parted variant of this problem. And the other possibility that we consider in this paper is that the variant is free-parted. So here we have three sets, and we ask if there are three numbers where first number comes from the first set, second from the second, and third from the third, and that they satisfy this linear equation. And so these variants are very similar, but the difference is that we either have one set or three sets, and in one set we require that these elements are distinct, and in free-parted variant we do not require that these numbers are different, because it may happen that these sets are not disjoint. Okay. So now let me define what are trivial and non-trivial variants. So clearly, let's observe that some combinations of the parameters alpha and t are easy to solve. For example, if any of the coefficients alpha I is 0, then we obtain an equation that is about not three numbers, but essentially two. So we have a linear equation about two numbers. So for one number, we can obtain what is the value, the target value for the second number. So we can iterate through all numbers in the set and binary search the second one. So this will be almost linear time algorithm solving that problem. And that's why we say that this is trivial. And the other variant that is easy to solve is when t is not 0, but the greatest common divisor of these parameters alpha 1, alpha 2, and alpha 3 doesn't divide t. Because then, as we operate on integers, we clearly have negative answers. So there won't be three elements from this set x satisfying this equation, because they are integers, and one hand side will be divisible by this GCD and the other will be not. So these are the variants that we call trivial, and all other variants will be non-trivial. So both one-parted and three-parted. And in this work, we show that all non-trivial variants of free LDT are subquadratic equivalent. And both free sum and average are non-trivial. So this theorem gives us they are subquadratic equivalent. And one corollary from this theorem is that average is free sum hard. So this answers this open question about the relationship between average and free sum. Good. So to establish this equivalence, we first show that all non-trivial free-parted variants are equivalent. So the proof is that we can scale and shift every set appropriately. So to change this coefficient t from 0 to something non-zero, we simply add numbers yi that satisfy this equation, and we can obtain these numbers from Chinese remainder theorem. and that's it. And similarly, if we want to move from from non-zero t to zero t, we only subtract twice. And when we operate on when t is 0 and we want to change alphas to some different coefficients beta, we simply rescale every set and need to remember that we operate on integers. So that's why we cannot obtain rational numbers. Good. So we know that all non-trivial tripartite variants are equivalent, and the remaining part of the talk will be about the equivalence between one and tripartite variants. And here we will we will not change the coefficients alpha and t, so they will stay the same during all reductions. Okay, so first let's show how to reduce one-partite variant to a three-partite variant. Because the easiest approach would be to set all sets A sub I equal to the set X. And clearly, if there is a correct solution, so there is a triple from triple of distinct numbers from set X, then we will find it, because each of them will be in each of these sets A sub I, and that's it. But the problem is that we cannot ensure that we do not take one element more than once. For example, in threesome, we could take one element twice and accept the following solution. So 4, 4, and minus 8. So here it doesn't correspond to three distinct numbers from the set X. And even worse, in average, we could take any element 3 times and obtain an arithmetic progression, because this is a proper arithmetic progression consisting of 3 occurrences of the same number. In this example, it is 4. So we cannot set all sets A sub I equal to the set X. But fortunately, we can use the technique introduced by Alon in 1995 called color coding, which simply provides us a way to find log squared n partitions of one set into three sets in such a way that every triple of elements is split between these 3 sets at least once. So that's exactly what we need. So that if there is a solution, so if there is a triple of elements from X, there will be an instance in which they are in different sets. So here we can use this black box tool by tool of color coding. So the more difficult reduction is the other direction. So when we want to reduce a tripartite instance to one-partite instance. And first, let me show how the reduction for threesome, because it is folklore and it would be a good intuition for the next steps. Because we multiply all sets by 8 and add a small constant to each of them. So to first set we add 1, to the second add 3, and subtract 4 from the last one. And this reduction ensures that if there is a triple of elements that sums up to 0 from the set X, then we need to take one element from this first set, the other from the second, and the last one from the third one. Because this 1, 3, and 4 are chosen in such a way that you cannot take 2 or 3 elements from one set and still obtain a number that is divisible by 8. And clearly 0 would have to be divisible by 8. But this is a reduction for threesome, and it doesn't necessarily work for different variants of 3LDT, but we will try to find something similar. So we'll try to find a constant C and other constants gamma I, which are good. What does it mean? It means that any solution consisting of distinct elements x1, x2, x3 from X satisfies that every element xi corresponds to an element of set A sub I. So that's what we need to achieve. And in particular, we'll require that the smaller order parts cancel out. So sum of alpha I times gamma I is 0. And there is a technical detail that some alphas might be equal, and we need to allow permuting x's with equal coefficients. So that's that we need to remember about. And when can we find such a good transformation? So when there are good coefficients gamma 1, gamma 2, and gamma 3. And in this lemma, we show that if t is not 0, or the alphas do not sum up to 0, then we can always find such good coefficients. And how do we do it? So we consider the three-dimensional space of all possible coefficients and write down a finite, actually a constant number of a finite set, so constant number of forbidden planes. So forbidden plane is this one which corresponds to taking two elements from one set, or shifting the order in the wrong way, or having some zero coefficients which we do not allow. And then we show that the plane that I mentioned in the previous slide, so sum of alpha I times gamma I equals 0, so that this plane contains at least one point with rational coordinates that doesn't belong to any of the forbidden planes. And then we scale this point up, and we obtain these good coefficients. So the only case which is not covered by this lemma is when t is 0 and the sum of alphas is also 0. And then we cannot hope to eliminate solutions that use three elements from the same set A sub j. So no matter what coefficients gamma we choose, we will always allow taking all three elements from the same set A sub j. And that's pretty problematic for us, because for example, this is the case in average, because then there are coefficients 1, 1, and minus 2, which sum up to 0, and t is also 0. So even for average, we have this problem. So yeah, this problem is that some set A sub j contains a solution to the given equation, because we cannot forbid taking all three numbers from one set A sub j. And to overcome this difficulty, we use Baronset, which considers progression-free sets. So a set is progression-free if it contains no three distinct elements from the set, such that they form arithmetic progression. And in 1946, Baronset showed that there exists a progression-free set of this size. So this is very dense in terms of the size of universe. So this construction, fortunately, can be easily generalized to avoid any fixed linear combination of this form. So because we do not focus only on average, but all variants of free LDT that were not covered with the previous lemma. And this comes at the expense of decreasing the size of the set to n divided by 2 to O square root of log n. So we change this constant here. And we call such set gamma delta 3. And the main trick that we use is that we'll partition every set A sub j into not too many alpha 1, alpha 2, 3 subsets A sub j uppers index I. And then we will run the previous reduction on every triple. So we will choose every possible set A sub 1 I1 and every set here and every here. And then we will make sure that there are no solutions inside one single set. So that's what we need. And how to apply Baronset to obtain a partition of a universe into a small number of sets. So we start with one set, and which is dense, and we know that it exists from Baron's construction. And then we will draw many shifts uniformly and random from this interval, and we obtain that there is a big problem. We have that probability that this that an element y from the universe is covered by this set q shifted by this delta, and then we repeat this procedure as c, which is w times log n times. So we have many random shifts, and this will be the collections of sets that we state that exist. So we take one Baronset and all its random shifts, and with that approach we obtain that there is a high probability that the sum of all these sets covers the whole universe. And there are also some technical difficulties that we overcome in the paper, because first we need to show how to construct this Baronset, not only use the fact that it exists. Then we need to remember that the universe is big. It's much bigger than the size of the input, so we cannot store the whole Baronset. We need to use its implicit representation. Then I told you that we use random shifts, but we will de-randomize it with conditional expectations. And we need to remember that our reductions sometimes increase the size of the universe. So we can also overcome this problem by reducing it to a constant number of smaller instances. And finally, we need to remember about the efficiency of our reductions, because the whole construction needs to be subquadratic. Otherwise, our reduction will be useless. So, but yeah, fortunately, we can overcome all these difficulties, and and they are all explained in the paper. But these were the main steps that we need to establish this equivalence between all non-trivial variants of free LDT. And in the end, I will say a few words about larger values of k, because probably you notice that some of the techniques that we said easily apply to larger values of k. So we can try to construct the similar reductions for k sum and see if this is also equivalent to other variants of k LDT or not. But unfortunately, not all our techniques apply, and the big problem is, which didn't appear for k equals 3, is a genus of a linear equation, because the genus is the largest number of groups, such that we can partition the coefficient into disjoint subsets, such that elements from every subset sum up to 0. And for k equals 3, the genus is always 1, but for larger k, this genus increases, and this makes it more difficult to find sets avoiding this particular equation. So, for example, the smallest example for k equal 4 is the equation that sum of two numbers is equal to sum of the other two numbers, and it is also known that there is Sidon set, which exactly avoids this equation, and it is known that it cannot be too dense. So this is one reason, or maybe the first step to approach this problem for larger values of k. So thank you for your attention, and I will be happy to answer your questions during the online session. Thank you.